So what I want you to keep in the back of your mind throughout this talk, and it's going to be kind of the central theme, we're going to be thinking about how we can capture classical computation. And when I talk about classical computation, I mean classical algorithms and data structures. So think things like sorting, searching, pathfinding, dynamic programming, data structures, and these kinds of things. And specifically because we are interested in deep learning approaches, we might be then interested how we can take some of these concepts from classical computation and then capture it using neural networks. And the rough overview of how this discussion is going to go is we're going to go through 4 key points, and I hope to take about 10 or 15 minutes for each of them. So I hope to first convey some thoughts on why we as deep learning practitioners should be interested in capturing computation. Once I've hopefully convinced you it's a good idea, we will have some discussion on how to actually build a neural network that captures computation. And then once we have some basic idea on the state of the art in the field, we're going to try to think of some ways in which we can strengthen the fascinating connection of neural networks with algorithms, as we'll see in some slides in the future. Those neural networks will actually usually turn out to be graph neural networks. And lastly, these tools will completely unexpectedly lead us to discover something that feels a lot like a type checker for graph neural networks. And I hope to also give you some ideas on where you can apply these concepts. So let's start and dive right into it. Some motivation for capturing computation. I'm going to start by posing you a problem that I want you to think about for a second. I'm going to ask you to find the optimal path from A to B. Okay. Now I know we have a very fun mixture of backgrounds at this particular event, so how you respond to this question may be quite different depending on your background. But if you are a theoretical computer scientist like myself, like my background is in theoretical computer science, it is very likely 9 times out of 10
efficient variation
that you will attack this problem in a very singular way, right? You're going to assume that when I ask you to find me the optimal path from A to B, that I've given you this weighted graph on which basically you have to find shortest paths starting from a particular source vertex to all the other vertices. And as we know in theoretical computer science, this is a canonical problem that you can attack using Dijkstra's algorithm or similar pathfinding algorithms, where you start from a graph like this, and after a few steps of computation, you can compute the shortest path tree, which is here highlighted in red. So these are all the edges that will tell you how to get from node 0 to all the other nodes. Okay, now the very act of you doing this, like saying that this is the problem I want you to solve, hides some potentially not so subtle assumptions. Namely, when we design these classical algorithms, usually what we actually want is to solve a real-world problem, right? In the real world, we're very rarely faced with abstract weighted graphs. We actually have, say, a real-world road network where we might want to find the shortest path from point A to point B or something like this. And the real world data that we're going to work with is not going to be given to us in this nice form. In fact, in reality, the real world traffic dynamics might be a high dimensional, noisy stream of data, which can be modulated by all sorts of things like changing weather conditions, traffic jams, traffic lights, roadblocks, and so on. And all of these things might make it very difficult to line them up to the problem on which you would apply Dijkstra. But actually, another very fundamental question here is, when I said optimal path, what does that even actually mean? Because if you want to find the shortest path from A to B, great, you're routing one particular agent in this road network to get to their target optimally. But what if, for example, you want to look at all of the agents in the road network and route all of them to their destinations so that you minimize congestion, you minimize pollution, and all of these kinds of things? This is now a whole level network optimization algorithm, which goes way beyond what just Dijkstra's algorithm can give you. So even like the assumption of you want the shortest path is a potentially not completely clear assumption. And okay, if we ignore the multiple algorithm problem for now, assume that by optimal I actually did mean shortest, you still have to perform this jump from the complex and high dimensional dynamics of the real world to an input on which you can actually apply the algorithm that you want to use. And traditionally, this is done heuristically or manually by humans. And it naturally invites the question, can we as humans ever hope to manually or heuristically do this kind of mapping? Well, basically, since the 1950s, it has been well known that the answer to this question is no. And this is actually one of my favorite algorithmic papers. It introduces the maximum flow problem, which is one of my favorite problems in theoretical computer science. And it's introduced in the context of studying railway network capacities and finding bottlenecks in railway networks. And right at the start of the paper, there is this particularly telling paragraph that says that evaluation of the railway system, so assigning a capacity to every single railway link, is to a considerable extent an art rather than a science. The authors know of no tested mathematical model or formula that would take into account all of the variables you need to take into account. And the final answer you get, no matter how intimately you're familiar with the underlying system you're trying to model, is largely one of judgment and experience, right? So it's been known from a very early point that trying to manually go from the complexities of real world to an input for an algorithm is something that's likely to be quite challenging or near impossible for humans. And as part of our neural algorithmic reasoning blueprint, we offer one way in which you could still salvage the computations of the algorithm and plug them into a real world problem of interest, rather than trying to go directly from raw inputs to inputs for an algorithm. You instead try to capture the algorithm in a high dimensional neural networks operations. So that would be the FPG pipeline here at the top. So I can synthesize a huge number of examples for Dijkstra's algorithm or something like this, and teach a neural network, like a graph neural network processor, to imitate the steps of that algorithm in this encode, process, decode pipeline. And this processor network now takes high dimensional latent states and maps them to different high dimensional latent states, such that at every step of the way, you can decode the intermediate states of the algorithm, okay? So now you've somehow managed to capture the high dimensional version of what the algorithm was doing, and that's what we mean by capturing computation. But once you have a module like this, which is a neural network that goes from high dimensional to high dimensional, this is a module you can plug anywhere, right? So now when you have the real world data on which you believe the algorithm could be applicable, you can take this pre-trained processor, freeze it, and then basically have a new encoder F tilde and a new decoder G tilde that allows you to decode back the outputs that you care about on the real world problem. So now you're dealing with your raw data through and through, and it's high dimensional, there's no bottleneck problems. And because you have the pre-trained processor in the pipeline, your model doesn't have to relearn the algorithm. It's there, it just has to learn how to use it, which arguably is an easier problem, right? And this is just a sample of the quotes from our original publication that just highlights what are the possible potentials of this method. So it might allow you to run classical algorithms on inputs that were inaccessible to them, like real world noisy inputs. It might allow us to adapt known algorithms to find more efficient and pragmatic solutions than the ones proposed by those of human computer scientists. And maybe in the opposite direction, since we're endowing neural networks with knowledge of algorithmic primitives, we might start to see some aspects of generalization that we see with algorithms, because algorithms trivially strongly generalize to arbitrarily large inputs, which neural networks typically don't know how to do well. We might actually be able to get better generalization in neural networks as a result of following these principles. So using the blueprint of algorithmic reasoning, you pre-train a graph neural network or an algorithm, then you deploy it on a natural problem. And I should just highlight that this is now no longer just in the realm of we believe this is possible. We actually have a few existing papers that show that this proof of concept could exist. And I would particularly highlight the X-Selvin paper, which was in Europe Spotlight a few months ago, where we showed in the very interesting case of reinforcement learning, which is full of algorithms that could solve the reinforcement learning problem perfectly if you had knowledge of the whole state action transitions, which you usually don't, right? So we pre-trained the graph neural network on a bunch of synthetically generated games on which you know the exact dynamics. We taught them to imitate the steps of these algorithms, and then we deployed the high-dimensional version of that algorithm inside the general agent that learns how to play Atari. Okay, and using this idea, we were able to get quite fun advances in data efficiency on very, very low data scenarios. And we have some extensions of this into the realm of self-supervised learning, the RMR paper, and most recently the SNAP paper, which also deals with continuous action spaces and therefore could have some applications in robotics as well. And I should just highlight that even if you choose not to follow our blueprint, so if you don't choose this pre-train on an algorithm deployed somewhere else, the benefits of thinking about building neural networks inspired by capturing computation can be quite impactful for science generally. And in particular, this proved quite impactful in our recent work on using machine learning and especially graph neural networks to uncover the interesting structure inside mathematical objects, and then using that structure to inspire pure mathematicians to go away and derive new conjectures and prove new theorems in very distinct areas of mathematics like knot theory and representation theory. And the significance of our findings was actually then recognized by the journal Nature, where a few months ago we were on the cover page. It was quite recognized in the popular press as well. And actually, our representation theory contribution was recently accepted by the top tier journal in representation theory. So we actually got a math paper out of all of this as well. But the key part, the graph neural network we used to analyze the objects in representation theory was directly motivated by an algorithmic approach that would solve the representation theory problem if we had access to privileged data. So we designed our graph neural network to kind of computationally mimic the steps of this algorithm. And as a result, we were able to get much better performant models and ergo models that we were able to interpret much better and uncover the structure much better. So just to reiterate, even if you don't decide to follow our blueprint of capture computation, put it somewhere else, building models that capture the relevant computation can still be a very impactful thing scientifically. Okay, so at the centerpiece of this pipeline, regardless of what you do with it, is this processor network P, which, you know, if we're able to build it properly, then we can unlock a whole amount of possible applications of classical algorithms. But, you know, there's the big question of how do we train models that learn how to execute algorithmic steps in a reliable way? So let's talk a little bit about our problem setup then. So there, I'll try to present in a very brief way the history of the most recent wave of trying to capture computations with neural networks. There were some previous efforts like neural Turing machines and differentiable neural computers, but like I believe this newest wave has a slightly different approach to this problem, and it's sufficiently distinct that it warrants a separate kind of discussion. And the whole bunch of recent efforts in this area are propelled on the assumption that graph neural networks align well with dynamic programming, which was one very impactful paper that was published by Keiluk Su and others from MIT at iClear in 2020. And they said, okay, like it turns out that if you algorithmically align to the problem you want to solve, you'll have much better sample complexity. So you'll be able to learn that algorithm much more efficiently. And in particular, if you want to learn dynamic programming algorithms, which is a very expressive language with which you can talk about basically all polynomial time heuristics that you care about, then you should use a graph neural network. Like that seems to align really well with dynamic programming. And this insight quickly made graph neural networks the main approach in this area. And here you see one pictorial illustration of how the computations of a graph neural network in latent space might align with the computations of a standard pathfinding algorithm, which is Bellman-Ford. Okay. However, like guided by this principle, many people went away and tried to throw vanilla GNNs at fitting algorithmic problems, and it quickly turned out that you cannot really do it very effectively with a vanilla GNN. And thus, there was a flurry of related work building specialized kinds of GNN architectures that fit one particular class of algorithmic computation. So iterative algorithms, data structures, auxiliary memory tasks, and coming up with all sorts of additional constraints on the model, like even having to carry a causal structure around yourself, right? So there's a flurry of related work that builds on top of this basic premise. And what this tells me, at least, is that there seems to be a lot of subtlety in alignments to computation. Like, it's not enough to just say you should use GNNs for this. You need to subtly adapt the GNN to the problem you care about. And whenever you have to do this without a rigorous theory to guide you, that means that you have gut intuition, which can often lead to guesswork. And as we know, guesswork can often lead to wasted GPUs, TPUs, and these kinds of resources. So maybe if we try to strengthen our theoretical foundations, we might also reduce the amount of guesswork in all of these related works in the area that explore different tiny variants, right? And okay, so let's see what the state of the art of the theory looks like, actually. So as I said, the presumption on which we prop up this exploration of GNNs to capture computation is the idea that GNNs align well with dynamic programming. However, if you look at the paper which introduced this, this idea, actually what they do is they show the code for the graph neural networks, and they show you the code for one dynamic programming algorithm, Bellman-Ford, and they argue that these two code structures look very, very similar, okay? And therefore, because they're very similar, they align. Now, I don't come from a theoretical mathematics background, but basically this argument to me does not feel rigorous enough to truly quantify where that alignment is coming from. It's very likely a correct observation, and obviously this paper has a lot of fantastic theoretical advancements in the field, but the specific observation that GNNs align with dynamic programming, we believe that that alignment is not sufficiently understood, and we need to work further. All the follow-up papers that build on top of this just cite it without providing additional context, at least from what we've been able to find so far. So this motivated us to try to relate these two concepts closer to each other. So let's try to get to know our two key players a bit better. On one side, we have graph neural networks, where we have graphs defined as tuples of nodes and edges. Based on those edges, you can define neighborhoods of a node, which are all the nodes connected to it with an edge. And you might represent features on this graph as some node feature matrix X, such that XU gives you the features of node U. And there's also potential for edge and graph level features. I'm just omitting them for now to keep things a bit more clear. And a typical graph neural network in the most general form might have the formula that you see here in the middle. So you update the features of each node by aggregating information across all of your neighbors. So you have this message function psi that takes the features of your node and the neighbor node and computes a vector to be sent across that edge. And then the receiver node aggregates all the messages sent to it, and then follows up with some update function phi to kind of update everything together. Okay, this should be familiar for those of you who have studied graph representation learning before. The second concept that we want to unify is the concept of dynamic programming, which is a general strategy of solving problems in this kind of divide and conquer manner, where you start with some problem X that you want to solve. What you do is at each step, you identify some sub-problems such that if you're able to solve them, you're able to solve X by recombining the answers somehow. And it turns out that this induces a very nice graph structure over your subproblems, right? Like you have problem X, all the problems that it's immediately related to are linked to it with some kind of computational edge. And in practice, you don't just continue recursing forever. A well-defined dynamic programming algorithm will always eventually reach a subproblem Y for which you will know the answer trivially, and that's called a base case. And then you can start from the base case in a bottom-up manner to compute the answer to the problem. And you can often conveniently express this in programmatic form, like the one I have in the middle of this slide here. Okay. So from a code structure perspective, it really feels like these two things should be related to each other because both of them operate over some kind of computational graph of vertices by sending messages across, right? And this becomes all the more clear when you look at one specific instance of algorithmic computation, which is the Bellman-Ford algorithm, which finds shortest paths in a graph starting from a source vertex. In this case, your subproblems are these DUs, the distances from the source vertex to a particular vertex U. And this is the equation of the algorithm. At every step, you update your belief of how far away a node U is by looking at all of its neighbors, seeing how to get to the neighbor plus the edge weight, and taking the minimum possible value, right? So this is a kind of natural way to iteratively build your belief of how far away a node is by just asking its immediate neighbors how far away they are. And you base case this algorithm by starting with the source vertex is trivially a distance 0 away from itself, and all the other nodes initially are not explored, so you give them something like plus infinity or a very large number, okay? So in this case, the set of subproblems is exactly the set of nodes in your graph, and your expansion function is exactly your one-hop neighbors. And this basically looks a lot like a special case of a graph neural network. So definitely there's some interesting alignments to explore here. One thing I'll mention is that you can even generalize this idea beyond the concept of shortest path finding. For some different definition of plus and minimum, you basically recover a specific semi-ring structure over your distances. And this connection is often used to motivate graph neural network architectures nowadays. For example, the neural Bellman-Ford networks that were published at NeurIPS a few months ago. Okay, so hopefully we now understand what we want to uncover, the connections between graph neural networks and the computations of these algorithms. And now let's talk about what are the tools that we can use for relating them together. First of all, why is it so difficult? Like, they have very similar code structure, right? Well, there is a very important technical obstacle, which is the number spaces that they operate over, and the character of the computations they do over them are vastly different. One simple example, graph neural networks operate over real vectors, and they typically use operations of linear algebra to achieve their computations, whereas algorithms work in the space of numbers with infinity to denote things you haven't reached yet, and then you have these interesting semi-ring structures around those numbers, right? So it's a very different character of computation, and it's hard to directly relate them. So what we actually need is a perspective that will let us study the structure of the computation, because the code looks very similar, right? Without looking at the specifics of how the data is manipulated, like what are the number spaces and so on. And it turns out, in our opinion, that category theory can offer us this particular perspective. Now, I understand that not everybody in this audience has come across category theory before. I've only started learning it a few months ago, so I'm very actively learning. I'm going to try to convey a few basic ideas about category theory so that you can follow along the key ideas. So, in a nutshell, category theory concerns itself with the study of categories, which are essentially collections of objects, and then you have morphisms that connect pairs of objects. So it feels a lot like a directed graph, right? And there's a few simple rules that these arrows must satisfy. There must be a unique identity arrow for every object. For any two pairs of morphisms, if one takes A to B, the other B to C, you must be able to create a composition, and that composition must be uniquely defined, and that takes A to C. And also you need to have associativity. For any three compatible morphisms, it doesn't matter if you first compose the first and the second one, or the second and the third one, you'll get the same result in the end. And one thing that's very critical about the setup of category theory is that these objects are just opaque objects. You cannot look inside them. You cannot ask what these objects are, okay? And this opaqueness of objects is what allows us to focus our attention just on the computational structure. So we look at the arrows, not the objects. And this means that it's a great recipe for discovering interesting connections like the ones we want to find, without thinking too much about what are the actual items that are being manipulated by these computations. And you might be asking yourselves, if we are to drop all that information about what's inside the object, aren't we being too vaguely abstract? Like, are we dropping too much information from the problem? And I'll show you a potentially mind-blowing example, if you've never seen it before, to show that actually this probably does not make the abstraction too strong. And to give you the example, I'm going to talk about the category of sets, which is a standard thing that every category theorist usually starts by studying. Basically, the set category, your objects are sets, and the morphisms, the arrows, are functions between them, okay? So this seems like a very general setting, and the sets specifically, you cannot look inside them. So you don't know what are the elements of those sets. You just see the arrows. Well, let's talk about this single element set, which I denoted with open close parentheses. This is the standard way. If you've ever done functional programming like Haskell, this is the standard way in which a single element set or unit would be denoted. And now you might ask yourself, if you look at any particular set A, what is the set of functions from set A to a single element set, right? And when you think about it, you realize there is exactly one function, right? The exactly one function that maps A to the unit element is the function that always returns the unit element for every possible input, right? And this structure actually allows you to uniquely say which object is up to isomorphism, the single element set. It is exactly the object for which no matter what other set I choose, there's exactly one morphism pointing into it. Okay, so already just by analyzing the structure of this graph of sets and arrows between them, I've identified which set has one element in it without ever peeking into it. I just looked at the arrows, right? And the amazing thing happens now. When I have a single element set and I know what it is, can I talk about the arrows from that set to another set? Because a single element set only has one element, every single function from it to some other set isolates one element from that other set, right? It's what we call a constant function. So if I have a set B that has 6 elements, 1, 2, 3, 4, 5, 6, there are going to be exactly 6 morphisms from the unit to that set. So after I've discovered my unit set, which was discovered just through analyzing its local structure, I can now use that unit set to tell you everything about what's inside every other set just by looking at the arrows. So at no point have I peeked inside B or peeked inside the unit set, yet just by looking at the arrow structure, I can tell you that B has 6 elements. Okay, so it's isomorphic to 1, 2, 3, 4, 5, 6. So this is one mind-blowing example where even though I've dropped everything that's inside the set, I can still detect patterns in computation without focusing on what's inside, because I can reconstruct what's inside by looking at the arrows. And this is what, in my opinion, makes category theory perfect for the kinds of purposes that we want to do here. Okay, so now back to our main event. What we're going to try to do is we're going to try to ignore the specifics about the data space that we're operating over. So we're going to try to define some latent space R, and we'll minimize the assumption over it as much as possible, and then plug the appropriate R to describe both GNNs and dynamic programming. And it turns out that this is okay to do because most of the behaviors we're going to care about, at least for now, to the extent of our theory, will arise by studying not R, but functions from S to R, where S is a finite set. So this means that our principal object is going to be exactly this set category that we talked about so far, and the category of then putting R-valued quantities over those finite sets. And what our aim is going to be is now to find some abstract object, so some composition of morphisms that's capable of representing both the computations of GNNs and the computations of dynamic programming, so that then we can tightly align them to one another. And what we propose is the integral transform. So let's talk about what this integral transform is. This is where kind of the meat of our theory will materialize. So the general setting that we find is going to be probably quite impactful here is this diagram known as a polynomial span, where you have 4 different sets, X, Y, W, and Z, and 3 morphisms between them. And specifically how to interpret this data, I'll show you concrete examples in a bit, but this is just the abstract diagram. W is the set that contains your input data, and Z is the set that contains your output data. So in some way, you want to send data from W to live on Z. And to get there, it must pass through some intermediate steps, which are the argument space X and the message space Y. How to intuitively think about this diagram is as follows. If I want to compute outputs, I compute them by aggregating several messages. This aligns well with both graph neural networks and the dynamic programming computation. So you need some space on which those messages will live. That's Y. And the map from Y to Z tells you for each message, which output is it being sent to. Then the message data is usually computed by computing a message function. So that's something that takes all the relevant bits of the input and computes the message that you care about for that particular message carrier. And the arguments for that function need to live on some space, and that space is what we call X, the argument space. So the second morphism, x to p, tells you for every single message argument, which message function is it being applied to, which message is it going to. Now, where do we get arguments from? Well, they're just appropriately copied versions of what we have in our inputs, right? So from inputs, we recover arguments for a function, then we apply a function, then we aggregate, right? So we have this final morphism from x to w, which is somewhat interestingly pointing what you might think is the wrong way. But actually what it tells you is it's denoting the fact that x is formed by taking copies of w, right? So the morphism from x to w tells you for every argument, what is the input that it came from? Okay, so that's why it's pointing that way. Now let's try to concretize this a little bit. So I put the diagram in the corner here, so you can always keep it in the back of your mind. Let's give a proper geometric example, which I'm sure will be appreciated by some of the audience, given that this is the School of Geometry. So imagine that I have data that lives on a circle and a line, right? So that's my input space W. And I want to do some transformations to it to obtain data that lives just on the line. That's my output space Z, okay? And I mean, if you want to be very naive about it, you could just say, let's completely ignore that the circle ever exists and just do a direct transformation from the line data to the output data, right? And that's certainly one way of doing it, but obviously it ignores half of your input space, so perhaps it's not wise. So instead, what we might choose to do is actually, let's think about what is some carrier data, some message data, which would be supported by both the line and the circle. And one convenient object for that turns out to be the cylinder, right? The product of a line and a circle, yeah? So what we're going to do is we're going to compute these messages that live on a cylinder. And we're going to then, once we have those messages, integrate over them to get the integrate over the circle to get the final output on the line. And this allows us to efficiently combine both of these inputs, right? But how do we compute those messages, right? We need to apply some kind of a message function over these two inputs. But to be able to apply that message function, we need to distribute those inputs to an appropriate cylinder, right? And that's where our argument space comes into play. What we do is we take the circle and the line, we broadcast their data, we tile it in neural network library terms so that it lives on these two cylinders, and then we perform a function over those two cylinders to get the message for that particular cylinder, okay? So this is hopefully a nice pictorial illustration of what these four sets actually mean from a geometric perspective. And I am well aware that, you know, this just talks about the relations between the sets. What we really care about is how to pass data along these sets, right? So to make the notation a little bit simpler, I'm going to use this shorthand angle bracket AB for the set of all the functions from A to B. And specifically, imagine now that I have data that lives on the input. So that's a function f that takes the input set w and gives you the values on those inputs. So that's w to r, which we denote by angle bracket wr. And we want to gradually pass data along this diagram to obtain some output data that lives on z, right? And what we do is we convert this polynomial span into what's called a polynomial functor, which is a standard categorical generalization of a polynomial, but we won't get into the details of that, which allows us to gradually move that data across the diagram. So the first step that we need to do is we need to copy the data from W to live over X. Conveniently, because our arrow from X to W points downward, it's actually very easy to go from a function you know, W to R to get a function of X to R. You just do simple composition with the input morphism, right? And this first operation, known as a pullback, is just the composition of your data with the input morphism. So any data you have on W, you just copy it in the appropriate place in R where it needs to go through composition. Okay. Now, you might be asking, once I have data that lives on X, I need to send it to Y. So can I do function composition again? Well, you cannot. These operations, known as push forwards, are tricky because the arrow, the P arrow, is pointing the wrong way. Yeah. To do composition, P would need to be pointed backwards. So generally speaking, you cannot do a simple composition to go from XR to YR. And therefore, we need to define these two push forwards, P times and O plus. And I'll first talk about the final push forward, so the one that takes Y to Z, because that one's a bit closer to what GNNs already do quite often. So assume we have data on our message space, so some functions from Y to R. And now we need to find some morphism that will face the right way so you can compose stuff. Well, one natural candidate for this is the so-called pre-image, right? It's kind of like an inverse, but for a function which is not a bijection, right? So the inverse of O would be this O to the -1, which gives you the set of all messages Y that's sent to this particular output. And of course, as mentioned, this has some issues because unless O is a bijection, this will now give you something in the power set of Y's rather than the Y's. And if you compose it naively with your message data, it will now give you a function to the power set of your values, and it won't even capture multiplicities, which is bad, because if you have multiple messages coming in that are valued exactly the same, you might want to take that multiplicity into account. So to explicitly handle this, we represent this as multisets of R, or bags, which is isomorphic to polynomial coefficients, polynomials with integer coefficients over R, which the integers just track how many times you have each one of these messages in the bag, okay? And once you have this formalism, now we can actually sort of define the first step of this push forward. So imagine I have a message function M, which maps the Y space to the reals. The first step of pushing forward along the O arrow is to compute basically a directed sum of all the messages in the pre-image, right? Now, this sum, you can treat it as a direct sum that counts multiplicities, right? So it just builds a bag of all these messages where if you see the same message twice, you just give it a coefficient of 2, for example, okay? And now once I have this bag of R's, I can reduce it to just one R using some aggregation function that looks at the bag and gives me just one R, okay? This idea of building a multiset and then having an operator that reduces it to just one value should be very familiar to people who worked with GNNs before, because this is the standard theoretical tool we use to analyze GNNs, right? We build multisets of neighbors, of neighbor features, and then we reduce them using a permutation invariant aggregator. And actually, this procedure is very, very similar for the second push forward, the one that sends arguments to messages. But one key difference, when you apply a function over arguments, the order might matter. So for this, a bag is not a good formalism because it drops the it has permutation symmetry, so it drops the notion of order. So instead, rather than using a bag, we will use a list to denote those kinds of data. Okay, and you might be also wondering how to be mathematically rigorous about our specific aggregator functions, which will take these bags and lists and produce single values. And we denote them by plus and times. This is quite related to, if anybody did any dependent type theory, the dependent sum and the dependent product. But basically, how do we define this plus and times? Generally, they must satisfy these axioms given by the commutative diagrams at the bottom, which people who have studied monads before might recognize. But fundamentally, what these axioms tell us is that plus and times must induce a semi-ring structure over R. So as long as our space of values can support a semi-ring structure, then we can define plus and times as the unique morphisms that close these diagrams and make them commutative, which means that no matter what path you take in the diagram, you'll end up with the same value. And now we can actually put it all together to have the full diagram of how data travels in our diagram. So we start from a function of the input space to these values. We pull them back along the first morphism to get data over arguments, XR. And then we push forward along the second morphism to first build a list of arguments for every single message. And then we use the times aggregator to compute the fold over that list to compute the actual message function. And then finally, when we have the message data from Y to R, we do a second push forward where we first collect the multiset of all the messages being sent to the particular output space. And then we reduce those messages using the plus operator. Okay, so this is generally the idea. And it's good to kind of illustrate how this all happens in a graph scenario, because we're going to be using this to instantiate graph neural networks. So it's a good idea to kind of relate the individual steps of this diagram to steps of computation in a graph neural network. So for those of you who haven't followed the maths too closely, this is a good opportunity to kind of pictorially understand what's going on. So I have a bunch of nodes, right, that try to send data to a central node B, and I have some features over the nodes. This f of d gives me the features of node D, okay? The first step, the pullback, let's say I want to compute a message over the edge from D to B. How do I compute that message? I typically need the data from my sender node and my receiver node, right? So the pullback operation pulls out those two relevant pieces of information and stores them for you in this convenient new function h, which identifies the two arguments. Once you have those two arguments, you can compute the message function by pushing it forward into the message space. So here the message space is the space of edges, and you compute the edge messages by reducing these two inputs. And finally, once we've computed in the same way in parallel all the different edge messages, you can now push them forward into the central node to update the representation of the central node. So these three steps are color-coded to correspond exactly to the three arrows of our diagram. So to pass information in a graph neural network, pull back the data for the sender and the receiver node, then push forward that data to compute the edge message based on them. And then once you have all the edge messages, push them forward into the receiver node. This is the general idea. And the reason why I made the green and red circles is because the push forward is typically not a bijective operation. So you will have multiple nodes sending into the same node, right? And then you need to have some way of reducing all that into one vector. And the way in which you do that is through the use of the aggregation function. And one thing that's important, I don't have enough time in this talk to go into detail on it, but this is a sufficiently expressive proposal to represent various kinds of computation. And for specific choices of these four sets, we have exactly re-derived algorithms like Bellman-Ford. I'll leave a link to the paper towards the end of the talk so you can look at the derivation in detail, but we've been able to extract exactly the Bellman-Ford equations from this diagram by choosing particular kinds of input spaces, message spaces, and so on. Here, V is the set of nodes in a graph, E is the set of edges in a graph. Okay, but now we can also do the same kind of exercise with GNNs. Here is a typical message passing neural network expressed using this diagram. Our input space is the space of 1 plus V plus C, right? Graph features, which is the unit set, plus node features, plus edge features, right? And then based on these three pieces of information, you compute messages which live on edges, and then those messages are integrated to compute outputs over the nodes. This is how typical graph neural networks tend to operate. And how do you compute those messages? You compute those messages by combining the data from the graph, the sender, the receiver, and the edge as the four arguments to a message function. So you broadcast these three sets into four different copies of E from which you can perform the reduction. And when you transform this diagram into an actual polynomial functor, which represents how data travels on a message passing neural network, you'll find that something looks very similar to what we did with algorithms. The main difference is that typically message functions can be deep. So you have this multi-layer perceptron arrow in there. And it's actually the key to generalize beyond what the algorithm does. But you must be carefully managing this MLP because, as we know, MLPs are universal approximators. So if they're left unchecked, they could skip entire parts of this diagram, and therefore you're no longer aligning to the computation that you care about. So this now finally lets us talk a little bit about what do we mean by type checking graph neural networks. Specifically, let's imagine that I don't want an output just over my nodes, but I want an output over my edges as well. For now, just to keep things a bit more convenient notationally, I'll set the edges to be V squared, so I'll assume a fully connected graph. And you know what 99% of graph neural networks do when they need to give edge outputs is they will just do a transformation that we see on this diagram here. So we still have a message space over our edges, but now we use it at the same time to reduce the nodes and to compute edge outputs. So the output space just gets an extra V squared, right? And this is done also in the GraphNets model that was proposed by DeepMind. And if you remember the fundamental properties of the set category, you can immediately start to see some amber flags being raised about this last function because it's actually no longer a function. you have to send exactly the same edge to two different places, right? To the node that it belongs to, the receiver node, and also to the edge output that you care about. So this is no longer a function. This is now a relation, and it's no longer a valid morphism in the set category, okay? Now, we should just take a moment to pause and ponder the possible significance of this result, because if a graph neural network doesn't pass the type checker in this way, like you have an arrow which is not functional, this does not mean you cannot implement it, right? All of these things can be implemented. And, in many programming languages, you can also write code without ever passing the type checker. However, passing a type checker is often a very important sanity check that your code is correct in the first place. JAX, for example, is a deep learning framework which uses something very akin to type checking to figure out that all the shapes of your deep learning model make sense and will actually let you compile. So what does this practically mean for those GNNs, right? Well, if you look at this previous diagram, your message on v-squared is now being used for two different things, right? It's being used to predict an output on the level of the nodes and also to predict an output on the level of the edges. And for the first one of those, it needs to be good enough to be integrated with all other neighbors, right? So you're repurposing the same message for two potentially very different purposes, right? And, from a representational perspective, this gives a huge amount of semantic pressure on that message vector because it needs to be used for two different things, right? And generally, this means that the type checker is telling us, hey, maybe you shouldn't be using the same message for two things, right? So let's try to come up with a different data flow, which will result in a v-squared output that won't reuse the message that we previously computed. And there's many different ways in which we can fill up this diagram. The specific proposal we use, which aligns well with some edge-centric algorithms, is that you compute edge-level outputs by first computing triplet outputs and then reducing over the receiver edge, okay? And the fact that you need to compute representations over 3 nodes at a time automatically induces that your argument space must have a v-cubed component from the graph, from the 3 constituent nodes, and the 3 possible edges connecting them. So it gives you a kind of 7 v-cubed space in the message function. Okay, and now we can sum up these two diagrams together, and now suddenly you have 2 different pathways in your graph neural network, right? One that results in your node outputs, one that results in your edge outputs, and everything is now still a valid function. You're not sending the same representation in 2 different places, and as a result, your GNN now type checks. This is not the only way you could have patched this, by the way. You can also put 2 v-squared in the message space, which would be equivalent to having 2 message functions, right? One to reduce the nodes and one to compute edge outputs. This would also work, but we just found that this would algorithmically align better with some of the algorithms that we studied in the context of fitting edge-centric computation. And surprise, surprise, when we patched up the model so that it passes the categorical type checker, we actually got this v-cubed model that was performing much better than the basic v-squared model that doesn't pass the type checker. And it was even performing so well that we could completely reduce its parameter count to go into this v-cubed small regime, and it would still outperform all of the v-squared architectures we were able to come up with over this collection of edge-centric algorithms from the CLRS benchmark that we recently published at ICML. So this is just a collection of learning to model various kinds of classical algorithms. And it seems like here the type checked version seems to perform better. And yeah, before wrapping up, which hopefully kind of gives you an idea on how category theory can, even after a lot of deliberation, lead to practical architectural recommendations. Some thoughts for what we might be able to do in the future. So previously, I told you when we looked at the arrows of this message passing model, there is this MLP arrow, which corresponds to the deep parts of the message function. And we haven't really dug into them, and looking at them properly might require you to be mathematically careful. So we might have to think more about the constraints induced by the task when modeling this. We also made all these pullbacks and pushforwards static because we assume that there's a predetermined graph structure available to us. But in the future, we might be very interested in looking at GNNs and dynamic programming algorithms that dynamically alter the computation by inventing new nodes, rewiring between the nodes, and so on. And it could be quite useful for situations where you need to figure out the subproblems as you go along and not assume that the subproblems are given to you at the beginning. And lastly, as I mentioned a few slides ago, category theory allows us to study the connections between objects without really diving into what's inside the objects. And as a result, you might discover some surprising connections. Our subsequent literature review led my category theory collaborator to conclude that similar kinds of polynomial spans and integral transforms can be used to rederive Fourier series, and also in particle physics, the Yang-Mills equations. So it could be quite interesting to at some point communicate with a particle physicist and try to see, has our attempt to unify GNNs and dynamic programming algorithms led to just a discrete instance of something that was already known in particle physics a while ago. This could be quite interesting. If you want to find out more, because obviously I couldn't go through the entire theory as part of this one talk, we have made our paper publicly available on arXiv, and the recent version just came out, so you should be able to find all the latest details in there. And it's been presented at 2 ICLR workshops. It's currently under review at NeurIPS, so we'll see how that goes. But yeah, we hope you'll find it interesting. And I hope you enjoyed the talk today. I'd be happy to chat more on Slack and otherwise if you have any questions. Thanks so much for listening. Thanks again to LOGML people for inviting me. And yeah, thanks so much.